Well, I hope everybody did a good job using our empirical rule to work with some of these normal distributions. And the empirical rule does a great job if we're lucky enough that every single value happens to fall on a nice z-score, like z equals 1, 2, 3, stuff like that. So, but in reality, in most cases, our z-scores are not going to be nice and easy. So it'd be nice to figure out how to calculate this area under the curve so we can get our probability for any single values that we want. And thank goodness for our calculator or Google Sheets, whatever you might have to be used. We've got this nice little command called normal CDF to the rescue that's going to allow us to do exactly like that. So with this one, it is similar to the binom CDF that we had before, but since this one is normal CDF, again, the CDF does stand for cumulative distribution function, just like we had before. But the normal obviously refers to the fact that we're using a normal curve for this one. Now, there are some advantages to this one over binom CDF. So if we look at the setup, notice our setup here is where the things we have to enter is we're going to put in a lower bound, an upper bound, a mean, and a standard deviation. Well, remember with binom CDF, it always counted with 0 and then went up to a certain value, which was great if we were doing a less than or we were doing a less than or equal to. But if we had a greater than or a greater than or equal to, we always had to do like that 1 minus binom CDF in order to make it work. Well, here, since we can actually enter a lower bound and an upper bound, this won't matter what kind of, whether we have a less than, a greater than, we'll be able to use all of these much, much easier, and we won't have to, hopefully make as many errors as we might have made using the binom CDF command and things like that. So I will show you how to deal with some of these with some examples and stuff. So let's go ahead and take a look first, just to find the value, just to introduce us to the calculator command and kind of see what's going on with these. All right, so we've got our little standard normal curve, and so we want to find the area under the curve to the left of z equaling 0.47. So what we're trying to do is we're trying to find the value to the left. So if we think about this in terms of an inequality, we're trying to find the x is less than 0.47. And so this is another nice thing. So it doesn't matter whether we're looking for less than or equal to, or anything like that. Whatever that value is always going to be the bound. We don't have to like go to 0.46 or anything like that. So regardless of whether it's a less than or equal to, whatever that number is going to be the upper bound or the lower bound. We don't have to modify the bounds like we did in our binom. So again, that's another nice feature of this one. So now with this one, since we're going to the left, that 0.47 is going to be our upper bound that we're looking for. But since we want this thing to go on and on and on and on forever, what would be like a lower bound for this? Well, what we want to do is we want to pick some ridiculously small number that's never going to happen in our data set. So with this one, we're dealing with numbers that are relatively small. So what I'm going to do is choose my lower to be something like negative 100,000 or negative 1,000,000, whatever. I mean, you can make this as big or as small as you want to, but we just want to make sure it doesn't look anything like our data. So our upper bound is going to be the 0.47. Our lower bound is going to be this negative 1,000,000 or negative 100,000, whatever you pick. So the way this is going to look when we type it in the calculator is we're going to get our normal CDF, our lower bound, so whatever small number we pick. Our upper bound is 0.47. And since this is our standard normal curve, our mean is going to be 0, and our standard deviation is going to be 1 for each of these. So we're going to comma our mean, comma our standard deviation. All right, so let's flip over to the calculator real quick so we can take a look at these. So if we go to our calculator here. So the good thing is the normal CDF is exactly where our binom CDF is. So if we go to second and vars, notice this time number 2 is our normal CDF. So we can grab that right away. And so again, just pick some ridiculously small number. So I'm putting in, I think, a negative 1,000,000. And then our upper bound was 0.47. Comma our mean, which is 0, comma our 1, which is our standard deviation. And then lo and behold, we get 0.6808 is our probability or area under the curve for that one. So 0.6808. So let me bring that over here. So we've got 0.6808, or if you want to think of it as a percentage, it'd be like 68.08%. And so that's just what we're going to do for each one of these, try to decide which one's the upper bound, which one's the lower bound. And again, if we've got, a trick like this where it's a strictly less than or a strictly greater than, we are going to have to make those upper and lower bounds ridiculously big or ridiculously small just to make sure we get accurate answers for these. All right, so for B, so we've got the probability to the right of negative 1.24. So we're looking for an x greater than negative 1.24. So with this one, that means that negative 1.24 is actually going to be our lower bound, which means we're going to have to make our upper bound something ridiculously big, so like 1,000,000 or 100,000, whatever you want to pick. And so again, when we put this in formula form, it's going to look like normal CDF, our lower bound, comma, our ridiculously big number, and then 0, 1. And so again, let's flip that over, type that in the calculator. So we've got a normal CDF, so negative 1.24, comma, some really big number, comma 0, 1. And so we ended up with, looks like 0.8925 for this one. So we got 0.8, oops, I'm going down to the next problem, hold on, sorry. So 0.8925 or 89.25% for this one. All right, so C is actually set up ideal for the way normal CDF works, because in this case we're trying to find the value between two different values. So this is exactly what we're looking for. So this means that 0.86 is going to be our lower, the 1.15 is going to be our upper. So we can just go straight to setting this up as 0.86, comma 1.15, comma our mean, comma our standard deviation. And so again, flipping this over to the calculator. So normal CDF, 0.86, comma 1.15, comma 0, comma 1. And so it looks like we get pretty small numbers, so 0.0698. So 0.0698, or again, 6.98%, if you want to think of this as a percentage. All right, so for the last one, this one's a little weirder, so because we're trying to find the interval outside negative 0.44 and 2.10. So if you think about this from like a graphing perspective, so negative 0.44 is going to be somewhere around there. And 2.10, 1, 2, is going to be somewhere right there. So we're actually looking for like this section over here and this section over there. So you could do this one of two ways. You could calculate the normal CDF below negative 0.44 and then the normal CDF above 2.10 and add them together, and that would work perfectly fine. Or you could calculate the probability in between them and then subtract that from 1 to get those outside probabilities. So again, you can do this either way. So I'm going to set it up as a 1 minus. So I'm going to do 1 minus normal CDF. And so my lower bound is going to be the negative 0.44. My upper bound is going to be the 2.10. And then again, I still have my 0 and 1 for my mean and standard deviation. So typing this in the calculator. So 1 minus normal CDF, negative 0.44, comma, now I forget, 2.2, I think, let's see. 2.1, sorry. 2.10, comma, 0, comma, 1, gives us, it looks like 0.3478. We've got 0.3478, or 34.78%. Oops. All right, so again, a little bit simpler than our binom CDF because we don't necessarily have to think, except for that last one, we had to think a little bit about that one. But again, we could have done this as two separate normal CDFs and just added our answer together as well. So again, main thing is think about what our lower bound is, what our upper bound is. If we don't have a lower bound, just make it really, really, really small. If we don't have an upper bound, make it some number that's really, really, really big. And then just throw them in the calculator and see what we get. All right, so any questions or anything about that one? All right, perfect. So for example 2, what we're looking at is the same idea, but with this one, we don't have our standard normal curve. So notice our mu is given as 20, our standard deviation is given as 4, and so, but we still want to do the same kind of idea. So for part A, what proportion of the population is less than 18? So we're looking at the probability of x less than 18. So again, that's going to be our upper bound, since it's a less than. And since we don't have a lower bound, we just want to pick something ridiculously small. So we're going to get normal CDF, negative, something really, really small, comma, our upper bound, and then our mean, which now is 20, and our standard deviation, which is 4. So I'll leave that for you guys to type in the calculator, so that way I don't have to keep flipping back and forth, and I think we've got the idea of that. But if you do have questions about typing in the calculator, definitely let me know. And then for B, what's the probability that a random constant value is greater than 25? So from an inequality perspective, that's going to look like that. And since it's greater, that 25 is going to be our lower bound. And again, we don't have an upper bound, so we're going to want to pick something ridiculously big for our upper bound. So what we're looking at is normal CDF of our 25, comma, some ridiculously big number, and then again our mean, which is 20, and our standard deviation, which is 4. All right. Any questions or anything about that? All right, good. So definitely message me or anything like that if there's anything you don't understand, but hopefully those don't seem too bad. All right, so the last thing we want to talk about here real quick is this idea of a continuous random variable. And so again, this is what I'd mentioned before. Since our normal distribution is continuous, we never first off talk about the probability that x equals a given value. So even though there is a normal PDF command, we're not going to ever use it, because if you think about it, if I try to find the probability that x equals, say 2 on a standard normal curve, well, if I were to draw out what that looked like at 2, so 0, 1, 2, well, the idea is exactly 2 is going to represent a single line. So when we're trying to calculate these areas, what we need is to think about it as a bunch of rectangles being added together. And if I just have a single line, well, I have height, but I have no width. And so since my width would be 0, it's going to end up giving me some kind of a result that doesn't really make any kind of sense or anything like that. So in reality, if I was trying to find the probability that x equaled 2, say, for example, instead of using normal PDF, what I would do is something like this. I would use normal CDF. And then what I have to do is give myself a little interval around 2. So I could go like a half a step lower and make my lower bound 1.5, and then make my upper bound 2.5. And if this was our standard normal curve, then we could get our 0 and 1. So if I was trying to find the probability of x equals 2 exactly, I know this, sorry, this is all over the paper here, but that's the trick that I'd want to do instead. So typically, we're not going to be trying to find an individual value, but we don't want to use binary or normal PDF like we did before. So we don't want to use normal PDF at all, so even though it's available. So we're only going to use normal CDF. And again, if we're trying to find an individual value, then we'll plug it in. So, all right, so go ahead, work on practice 1, practice 2, and then we'll come back in a little bit and we'll talk about going backwards, trying to find the inverse norm for these.